Hello, my name is Chris Gordon and I'm a product scientist at Optronic Laboratories. Today I wanted to dive into the IEC 62471 standard on photobiological safety for lighting and lighting systems, as well as the instrumentation that OLI has available to ensure proper compliance with this standard. Before I get too far into that, I'd like to give you some background on Optronic Laboratories. OLI was established by two former NIST scientists in 1970 who modeled both their facility and practices after NIST. They quickly achieved a reputation for excellence in both light measurements and calibration. For over 50 years, OLI has been improving the way the world measures light with our spectral radiometers, integrating sphere systems, and calibration standards and services. Until recently, lamps and lighting systems were widely manufactured with little safety oversight or restrictions, particularly now with LEDs being produced in spectral regions that are potentially dangerous and with high output power over a very narrow spectral band. It became necessary for the international community to develop a set of standards and classifications to assess the potential hazards a light or lighting system could pose to those who are exposed. The objectives of the standard were to both evaluate and control the optical output of lamps where humans are exposed relative to the potential photobiological hazards. In order to assess the possible risks of a light source, a spectral profile has to be taken. So in that vein, the standard also sought to prescribe the necessary spectroradiometric measurements and techniques that are necessary to evaluate the spectral hazards under well-defined and relevant conditions. The techniques that are involved are Radiance and Irradiance, and I'll discuss them in more detail later. Some of the possible light sources may be complex lighting systems and also involve filtering and projection techniques that could alter the spectral profile. But the aim of this standard is to evaluate the light or system at the point of human exposure. There are several factors that contribute to the extent of the possible hazards a light system poses. These factors include the wavelength or wavelengths emitted by a source, how much of that light is being seen, or in other words, the field of view or angular subtense, how sensitive human physiology is to different wavelengths, and how long the exposure time lasts. In order to have relevant measurements, the experimental conditions need to reflect the physiology of the anatomy involved. In this case, it's the cornea of the eye, the skin, and the retina. As you can tell by the graphics so far, several measurements are geared towards the eye and the potential damage various wavelengths pose to the outer and inner eye. So it's not that much of a surprise that several of the experimental geometries are based on the anatomy and physiology of the eye. Now, I'm by no means a physiologist, but a brief mention of the eye's anatomy is pertinent to this discussion. Many of the hazards and measurements involve the retina, which is the part of the eye that detects light. It's connected to the optic nerve and lines the inner surface of the eye. It's shown here as a pale yellow color. Light enters the eye through the pupil, which is the opening in the iris, and is focused by the lens along with previous surfaces onto the retina. It's this focusing that adds additional danger as it concentrates the energy that's present to a smaller spot, and that increases the energy density. The outer surfaces of the eye are susceptible to different types of hazard. The relevant superficial parts of the eye shown here are the cornea, which is the white part of the eye, and the fine outer layer called the conjunctiva. You may have heard this in reference to conjunctivitis, which is an irritation of this fine outer layer. We'll come back to these types of hazards in a bit, But first I wanted to discuss retinal hazards. The amount of light that enters the eye is dependent on how big the pupil is. We know that the pupil can constrict and dilate. The average maximum constriction is to a diameter of about 3 millimeters, and the average maximum dilation is about 7 millimeters. These diameters are used as the limits for the field of views used in these measurements. For exposures with visible light, it's assumed that the pupil will be constricted, so a field of views corresponding to 3 millimeter pupils are used. With small sources or wavelengths that are outside the visible range, it's assumed that the pupil will be fully dilated, so field of views corresponding to a 7 millimeter pupil are used. In addition, the time of exposure and human physiology also help to determine the relevant field of view. For times up to a quarter of a second, which is how long the blink reflex takes, the eye is for all intents and purposes stationary, and the field of view is determined by the smallest spot the eye is capable of focusing to. This corresponds to a field of view of 0.0017 radians, which is about 0.1 degrees. For longer exposure times of 10 to 100 seconds, rapid eye movements, or REM, start to spread the exposed area of the retina out, corresponding to a larger field of view of 0.011 radians, which is a little bit more than half a degree. For significantly longer exposure times, greater than 10,000 seconds, typical vision tasks like reading move the eyes such that the exposed area of the retina is spread out much further to a field of view angle of 0.1 radians, which is a little over 5 degrees. For exposure times that are in between these periods, the standard states time-dependent equations that can be used to calculate the corresponding field of view angle. These are shown in the red sections in the table here. For external or superficial exposure to the skin, conjunctiva, cornea, or even the distal surface of the lens, the exposure limits that are determined for very small angles apply to angles extending up to 1.4 radians or 80 degrees. This is due to various physiological factors that the standard itself doesn't go into. Nonetheless, this larger and easier angle to obtain is used for these measurements. As I mentioned on a previous slide, one contributing factor is the body's physiological response to different wavelengths. To account for this, the various raw measurements that are taken are multiplied by the relevant spectral weighting function to ensure that wavelengths that cause higher potential damage are weighted heavier than those that do not. The purple plot is used for the UV hazard associated with the skin and superficial surfaces of the eye. The blue plot is used for the retinal response to blue light, as well as the remaining visible wavelengths. The red plot is used when determining the retina's thermal response to broadband radiation from the visible to the near infrared into the shortwave infrared regions. I know this has been a lot of information so far. For me, what I found to be one of the most helpful parts of the standard are two tables that are found in section 5 of the standard, shown here, that essentially sum up all of the experimental measurements that need to be performed if you want to be fully compliant. Table 5.4 displays all of the irradiance-based measurements that correspond to hazards associated with the skin and superficial parts of the eye. The table separates the measurements into each individual hazard, shows how that hazard is calculated, over what wavelength range the measurements are to be made and the associating hazards to be calculated, the time scenarios that the exposure limits are divided into, their corresponding field of view angles, and finally, how the exposure limit is calculated. Table 5.5 displays all of the radiance-based measurements that are associated with the hazards of the retina. Like Table 5.4, Table 5.5 also displays the hazards, how they're calculated, and the corresponding wavelength range. What you'll notice is that the field of views are more numerous due to the various pupil orientations, and the field of view increases due to related eye movements over periods of time. As mentioned on a previous slide, for time intervals that are in between the defined times, a time-dependent term is added to each field of view angle to account for the additional time up until the next definition. I've mentioned irradiance and radiance measurements a couple times so far, and I think to further understand the instrumentation involved, a brief description of these measurements is needed. Irradiance and radiance measurements are two of the most common measurements taken of light sources and are the only two techniques that need to be employed in order to comply with the IEC 62471 standard. The heart and soul of the OLI IEC 62471 measurement system is the 750D double monochromator. The OL 750 comes both as a single monochromator, shown here in the image, and as a double monochromator. Since the IEC 62471 standard requires measurements down to 200 nanometers, a double monochromator is essential due to its high stray light rejection. The presence of stray light is one of the highest contributors to measurement error, particularly in the UV region where detectors are less sensitive. The OL 750D double monochromator has a relatively small footprint and doesn't take up much space on an optical bench. Its dimensions are 27.75 inches long, 16.28 inches wide, and 9.5 inches tall. The input and output ports on either side of the monochromator stick out a little over an additional inch. A monochromator, as the name implies, is an instrument that takes a mixture of wavelengths through the entrance port and selects one of those wavelengths to propagate through and out the exit port. The OL 750 has an F number of 4 to maximize the amount of light that's collected. The double monochromator, or 750D, has industry-leading stray light rejection that's more than 8 decades below the signal of interest. For those that are new to spectral radiometry or spectroscopy, I wanted to briefly go through how light propagates through the 750D double monochromator. The main functioning component of any monochromator is the grating. The 750D double monochromator comes with 2 tri-grating turrets that contain identical gratings on both sides of the monochromator. There are a variety of grating options available that span a wide range of available wavelengths. Customers also have the option to purchase additional interchangeable mounts with gratings that further expand their measurable range. Used in the 750D IEC 62471 measurement system is a plug-in chopper with associated lock-in amplification electronics. This AC detection system is essential in the infrared region where signal is limited and is very useful in the UV region where signal strength can also be low. In short, the chopper breaks the input signal into on and off sections that repeat at a constant frequency. The lock-in amplifier uses the same frequency to amplify the signal when the chopper is, quote, on, and ignore it when it's, quote, off, which serves to separate the signal of interest from any background signal present. The OL750 software platform also allows the user to adjust this chopper frequency. In order to increase the accuracy of the measured signal, the OL750D also has an automated 11-position filter wheel that contains filters that block out second-order harmonics that show up in the region of interest. It also has a closed position that is used to determine the dark current for each measurement. Light is collected by the appropriate collection optic and enters the entrance slit shown here on the right side and is collimated by the first concave mirror. By collimated, I mean that all of the light is parallel. The collimated light off the first concave mirror strikes the first grating. A grating is a wavelength selector, and different wavelengths come off the grating surface at different angles. This grating is rotated to a specific angle that selects one specific wavelength to continue propagating through the monochromator. In this example, green light is selected and collected by the second concave mirror. This second concave mirror then focuses the selected wavelength through an intermediate slit, shown here as a circular aperture, which is then collected on the opposite side by a third concave mirror. This mirror collimates the light again and directs it onto the second grating. This grating is synchronized with the first grating so that the same wavelength is chosen. The second grating spreads out the light a second time by the same amount as the first grating. This has a cumulative effect to get twice the separation, which increases the spectral purity of this selected wavelength. What I mean by that is that there are fewer wavelengths that are allowed through on either side of the selected wavelength. The term for this range of wavelengths that passes through is called the spectral bandpass. This bandpass is a function of both the gratings being used as well as the slits or apertures that are chosen. The variety of slits that come with the 750D monochromator allow for a wide range of selectable bandpass options. The desired wavelength is then focused through the exit slit of the monochromator after passing through the appropriate second-order blocking filter. The exiting light in this case is then detected by the appropriate detector for that wavelength range. In other configurations, there could be a variety of different optics prior to that detector, or just optics if the monochromator is being used as a monochromatic light source. The choice of input optic and detector depends on the type of measurement being made, whether it's radiance versus irradiance, and the wavelength range being measured, respectively. In order to understand why each optic is chosen for each measurement type, a description of each measurement type is needed. I'll make it brief, but if you have any additional questions, please don't hesitate to contact me. The measurements that are associated with retinal hazards depend on how much of the light that's emitted from a source is collected and seen by the retina. Light that enters the eye is limited by the diameter of the pupil. The associated measurements for these hazards are radiance measurements. In short, radiance is a measure of how light is emitted from a source. These measurements require a very well-defined field of view. This field of view is defined by two parameters: the distance from the light source to the collection optic, and the circular aperture with a well-defined diameter. The latter is what defines the cone of light that is analyzed. And this cone of light is described by a two-dimensional angle with units of sterradians. And that's why every value of radiance that you see is expressed per sterradian. Since the accuracy of the focal distance and circular aperture are of high importance, a telescope is normally used as the collection optic for radiance measurements. The telescope that's used in OLI's IEC 62471 radiance-based measurement system is the OL600 Direct Viewing Imaging Optics Module. The field of view aperture wheel has apertures selected to work specifically with two camera lenses in order to achieve the prescribed field of views in the standard, specifically those in Table 5.5 shown earlier. These apertures are easily selected using a dial that's on the side of the telescope. The image and diagram shown here has a viewer eyepiece on the top of the telescope that can be used to see the telescope's field of view. The OL600 that's configured for IEC 62471 measurements has a CCD remote viewer that displays the telescope's field of view through OLI provided software to facilitate easy source alignment. The image of the field of view comes from all of the collected light that does not pass through the selected aperture. This allows the user to see specifically what portion of the telescope's total view is actually being measured by the system. The OL600 also has a retaining ring that allows the telescope to be easily mounted directly to the 750D monochromator. I'll use a 3D rendering of the OL600 telescope to show how the telescope works. This view is looking down at the top of the telescope so that the CCD viewer is on the top and the field of view aperture dial is on the right side. The generic lenses here would be the two lenses designed specifically for the IEC 62471 compliance. In radiance measurements, light is emitted from a source, which is shown here as an X, is collected at a specified distance from the source, which is determined by the focal length of the selected lens. The cutaway drawing shows what's going on inside the OL600 telescope. The mirror, shown here as a square, is actually a round mirror that has selectable circular apertures. The light that does not pass through the aperture is imaged onto the CCD remote viewer and displayed on OLI-provided software. The selectable aperture appears as a black circle on the image and can be specifically placed in order to ensure you're measuring the portion of the image you intend to measure. The portion of the image that passes through the selected circular aperture is then imaged onto the entrance slit of the 750D monochromator to be analyzed. The OL600 is coupled directly to the entrance port of the 750D monochromator. The appropriate detector is selected based on the wavelength range being measured and couples directly to the exit port of the 750D. These three items together comprise a complete spectral radiometer configured for radiance measurements. The hazards involving radiation that impacts the surface of the skin or the superficial surfaces of the eye involve irradiance measurements. You can think of irradiance as the opposite perspective of radiance. In irradiance measurements, you are measuring how the light from a source impacts a surface. More specifically, you're measuring the energy density of the light when it impacts that surface. Irradiance measurements are performed using an appropriate cosine receptor, which is capable of accepting light from a 180-degree field of view. Typically, this cosine receptor is an integrating sphere, such as the OL-IS670 6-inch integrating sphere. An integrating sphere has a highly reflective coating on its inner surface. The light that's collected bounces around inside the sphere several times and produces a very uniform output. The IEC 62471 standard requires that measurements be made at a distance that produces an illuminance of 500 lux, but not closer than 200 millimeters. To allow for ease of use for these measurements, this IS670 comes with the option of a built-in photometer that allows the user to monitor the illuminance in real time as the source is positioned to ensure the required 500 lux. Just like with the OL600 telescope, the IS670 integrating sphere couples directly to the input port of the 750D monochromator. Along with the appropriate detector for the wavelength range being measured, these three items comprise a complete spectroradiometer system configured for irradiance measurements. The system designed specifically for IEC 62471 compliance has a field of view attachment that attaches directly to the IS670's input, which has the appropriate apertures to attain the required field of views specified in the standard, specifically in Table 5.4. The number of calculations that need to be performed can certainly be daunting. At OLI, we want to make the process as user-friendly as possible. To that end, we have developed an Excel template that is tailor-made for IEC 62471 compliance. The measurements that you made with the 750 system software are exported directly into the raw data from OL 750 tab of the spreadsheet, where it is instantaneously plotted. The spreadsheet has separate tabs for radiance and irradiance calculations to ensure that the calculations are easily organized and can be quickly identified and searched. Each individual hazard has its own column, which incorporates the appropriate spectral weighting function, which can also be viewed individually in their own tab. The columns each have a cell that shows the integrated value over the associated wavelength range, as well as the calculated exposure limit. For reporting purposes, there is an Output Summary tab that has all of the relevant calculated values, as well as the individual pass-fail results. In summary, the objectives of the IEC 62471 standard were to evaluate and control the photobiological radiation hazards from lamps and lamp systems at the point or points of human access by standardizing the measurement techniques required for evaluation. The standard takes into consideration photobiological hazards associated with skin, superficial surfaces of the eye, as well as the retina. The OL750D IEC 62471 platform offers all capabilities required to measure, analyze, and report the quantities required by the standard. The modular and flexible design of the 750D platform allows easy transitions between required radiance and irradiance configurations, as well as future adaptations for applications beyond the IEC 62471 standard without the requirement of a brand new system. I wanted to thank you for taking the time today to listen to this webinar. If you have any additional questions about the IEC 62471 standard, its associated measurements, or how OLI can help meet your spectroradiometric needs with our variety of NIST traceable calibration standards, spectroradiometer workstations, or myriad of accessories, please do not hesitate to contact me. Thank you.